Hi. Let's study inequalities. We'll study inequalities in various stages, different parts. I would start with linear inequalities. Then I'll go in for modulus inequalities. Then I'll go in for quadratic, cubic, quotient, general one, quotient inequality. Then we go in for graphical approach. Graphically, how do we solve the inequality? And as we are solving this problem, we will take up the word problems, also practical problems involving inequalities. To begin with the first part, that's linear inequalities. Before we begin, let's see some of the notations, symbols, etc. Intervals. Intervals are of two kinds. One is closed, and the other one is open. And we also have something called semi-open and semi-closed. That just comes in closed and open. Let's say I talk about set of all values of x between 1 and 2, not inclusive of 1 and 2. Set of all real numbers between 1 and 2 are infinite, you know that. Between any two real numbers, there are infinitely many real numbers. So if you represent that by number line, on the number line, we'll represent them to be 1 and 2 here, circle, circle, and darken the area. Darken the area here. But do not darken 1 and 2. This indicates all the values between 1 and 2, infinitely many values between 1 and 2, not including 1 and 2. This is negative infinity, and this is positive infinity. Yeah. So we write this one as x belongs to open 1 and 2, 1 comma 2. The round brackets here are read as open interval. These are used for open interval. We see that's the open interval. Open interval is an interval of real numbers, set of real numbers between the two given points, but excluding the end values. So open 1 and 2. So let's see, I have the second one here. That is, let's see, set of all values of x between 1 and 2, but including 2 and including 1. We represent that on the number line by marking 1 and 2 like this. And you can circle this. You can circle this, but you also got to darken this, indicating that the value 1 is included, the value 2 is included, and you got to also darken the area between 1 and 2. All the values between 1 and 2, including 1 and 2. That's called the open interval. Sorry, that's called the closed interval. I will write as x belongs to closed 1 and 2. So the square brackets indicate it's a closed interval. When you draw these square brackets here, it shows that you are talking about the interval where all infinitely many values are included, and including the end values. This is called the closed interval here. Right? And supposing you have the values like this. Let's say you're talking about set of all values of x, which is more than 1, but less than or equal to 2. I can call this as semi-open or semi-closed, where you find that x belongs to open 1, but closed 2, where I can indicate that on the number line as negative infinity, positive infinity. This is, let's say, 1, and this is 2 here. So you have a 1 and you have a 2. We darken the 2 here. You circle the 1, and then you shade the region between 1 and 2 here. And this is just left open. This is open, hole, and that's 2. 2 is filled, the hole is filled here. This is called you can call it semi-open or semi-closed. So basically, open and closed intervals are the ones which tells you whether open interval says that it's all the real numbers between the two given numbers, excluding the end values, and closed interval is set of all values, infinitely many real numbers between the two given numbers, which are including the end values here. You may also have the values, let's say x less than, let's say 5. X less than 5 will be, there's no boundary for this one. When I say x less than 5, suppose this is 5 here, negative infinity and positive infinity. When I talk about x less than 5, I actually talk about 5 less than 5 is all the values which are lesser than 5. It goes like this. I could just draw a little arrow here and say all the values to the left of 5. It goes on and on and on and on. We could also write this one as x belongs to negative infinity to 5. 5 is open. We never close the infinity or negative infinity because it's a number which you cannot possibly catch and put it in the closed bracket. It's a value which is, very, very, very small on the left side. We don't even know what that value is. And infinity is a large value, larger than anything. So we can't possibly catch that value and put in the closed interval. It just left as an open interval. So we just write as open interval at infinity or minus infinity. It's kind of funny to include the infinity or minus infinity in the closed bracket and say, okay, that's also included. That's a value which we don't know. That's a small value or the large value. So whenever it comes to infinity or minus infinity, we always leave that end open. Suppose we say you have x is less than or equal to 5 or something, then I could write this one as x belongs to negative infinity until 5 maybe. If I have x is more than or equal to 7 maybe, I can write this one as x belongs to closed 7 and open infinity. So remember, the smaller value is always written on the left side here, and the larger value is always on the right side here. Smaller value anytime on the left side, and the larger value on the right side. Smaller, larger. So this is about the closed or the open intervals. Another thing I want to revise talk about is the words which are often used. At least and at most. When I say at least, I mean that more than or equal to. Give me at least $5. So the money you should give me is more than or equal to $5. Give me at least a week to complete this project. So the time that I require is more than or equal to a week. A week is 7 days, so more than or equal to 7. So at least means that more than or equal to. And we have something called at most. At most is to mean not greater than. At most, 5 people can attend this function. So the number of people is equal to the number of people is less than or equal to 5. At least 4 people can come in my car. I don't want to get into troubles on the road, police will catch. So the number of people in my car is less than or equal to 4, which means that you may not, none of you may come, or one of you can come, or 2 of you can come, or 3 of you can come, or the maximum 4 of you. So if you're 10 of you are standing there and requesting, to for a ride or something, so it cannot be more than 4. So that's about less than or equal to, and more. And that's the meaning of at least and at most. I suppose that's simple English. Yes. Now we're going for so-called the inequalities, linear inequalities. As we already used inequalities, these are equalities lesser than or equal to more, or more than or equal to. These are called inequalities, where this can be called as an equality here. Okay. So talking about the inequalities, the basics first. Supposing you have, let's say, 5 less than 10. Of course, not supposing. 5 is less than 10. So supposing I add a positive number, let's say I add 2 on both the sides. I add 2. So 5 plus 2 and 10 plus 2, you'll find that this is still smaller than 10 plus 2, which tells you that if I added a positive number on this either side of the inequality here, the inequality is not disturbed. So even if I add it, subtract it, supposing, let's say, I subtract, let's say subtract 3 here, subtract 3 on both sides. 5 minus 3 and 10 minus 3, you find that 5 minus 3 is still less than 10 minus 3. So we subtracted a positive number on both the sides, the inequality is not disturbed. Supposing you multiply the number inequality by, let's say, 10. Let's say you multiply this one with 10. You'll find that 5 multiplied by 10 will give you 5 times 10 here, and 10 times 10 here. You'll find that this is still less than so much. So if you multiply it by a positive number on both the sides, the inequality is still not disturbed. If you divide by, let's say, 10, then you'll find that you have 5 by 10 and 10 by 10. Obviously, 5 by 10 is half, 10 by 10 is 1, so this is less than. So if you divide by a positive number also, the inequality is not disturbed. So if you added or subtracted a number, the inequality is not disturbed. If you multiplied and or divided by a positive number, by a positive number here, the inequality is not disturbed. So supposing I try, let's say you have 5 less than 10, and I multiply by -2 on both the sides. So you have 5 times -2 and 10 times -2 here. You find that -10 and -20, if you look at, on the number line, if you see, maybe this is 5, this is 10 here. Maybe this is -10 and this is -20 here. You certainly know that -10 is greater than -20. The number on the right-hand side, on the right, on the number line is always greater. -10 is more than -5. So inequality has switched. So you'll find that this is no more lesser, but this is more than this. This is more than this. The secret is whenever you multiply or divide whenever you multiply, in this case, for example, if you multiply by a negative number, the inequality will not keep quiet. It'll immediately switch. So inequality reverses when you multiply by, reverses when multiplied by a negative number. Look at this one now. Again, this is the multiplication. Supposing I go for dividing the number by, let's say I divide by -2, for example. Find that 5 upon -2 and 10 upon -2 here. This is minus 2.5 and this is minus 5. You find that 5 was less than 10. 5 was less than 10, but you'll find that minus 2.5 is more than minus 5. This is 0, this is minus 2.5, and this is minus 5 here. So obviously, minus 2.5 is greater than minus 5. So inequality switches around when you divide both the sides by a negative number. The inequality reverses. So I can say that the inequality reverses when divided by negative number. So don't say it's fair, I divide both the sides by the same number, so then the inequality should not be disturbed. No, it does get disturbed when you divide by or multiply by a positive, but they get by a negative number. Whenever you divide or multiply by a negative number, the inequality immediately reverses. So that's the main thing that goes on the whole lesson, basically, that the main thing that we learn is that whenever you multiply or divide by a negative number, the inequality always reverses. So if you have A is less than B, then negative A, you can say, is more than negative B here. If you have, let's say, 2 is less than 3, but -2 is more than -3. So if you multiply both the sides by a negative number or negative sign, the inequality will reverse. If you have, let's say, A is less than B and K is a positive integer, positive number, real number, so you'll find that minus KA is more than minus KB here. If you have, let's say, if A is less than minus B or something, then minus A is more than plus B. So whenever you switch supposing, let's say you have 2x is 2x plus 3 is, okay, let's take an example and understand that thing there. But then remember, the main thing that we have in this one is that the inequality is undisturbed if you add it both sides by inequality by a positive number, if you subtracted a number, if you multiplied by a positive, or if you divide by a positive. But if you multiplied or divide by a negative, the inequality will immediately switch around. Now going to solving simple equations. Solving simple inequalities. Let's say the question is that solve means find the values of x basically. So 2x plus 3 less than 5. Someone says that less than 5, solve in set of natural numbers in the set of integers, let's say in the set of whole numbers, and let's say set of reals or real numbers. Usually when they say solve, it goes without a say that they are asking for solving for set of real numbers, because if they want you to solve in a specific set, in a special set like natural numbers, integers, whole numbers, or some specific set, then they will always mention. Otherwise, solve means that keep it general and solve it in real numbers. So for this question, I'm going to take up in these different cases, but then then otherwise solve would always mean that you solve on the set of real numbers. Yeah. So let's say you have the first one. You have 2x plus 3 is less than 5. I can transpose. Transposing is basically mean that you subtract 3 on both the sides. That's the meaning of transposing. So plus becomes minus. So if I have 2x is less than 5 minus 3, I won't even write this one. Like addition becomes subtraction. So when you transpose by way of addition or subtraction, you should not have any problem because subtracting on both the sides does not disturb the inequality. So you have 2x is less than 2, therefore x is less than 1. Okay. So if you are looking for the set of natural numbers, so you'll find that the solution in the set of natural numbers is actually a null set because you don't have any natural number less than 1. So you can write like this, or you can say solution set is a null set. So they ask you solve for natural numbers. In this case, I found no natural numbers. Had it been less than, let's say x less than 5, I would write the elements as 1, 2, 3, 4 maybe, but I have none here. Let's say going for the second one, the same thing. They're saying that we arrive at 2x plus 3 less than 5. So 2x less than 5 minus 3. Therefore, 2x less than 2. Therefore, x is less than 1. So they're asking for the set of integers. I'll say the solution set is I can say dot minus 3 minus 2 minus 1 and 0, because all these are integers. Dot says that it is goes on like this. I couldn't possibly write, you may think that, oh, could I have written this one as negative infinity to 0 or something? No, a big no, because that's only a notation for the real numbers, infinitely many real numbers. But if it's a discrete set, the set of integers or like this, you have to list the elements like this, or you'd write another form like set builder form or whatever. But then the best thing is that right now, we will put it this way. Suppose they asked you for set of solution set in the set of whole numbers, the solution set, the set of whole numbers will be just a 0. And if they asked you the solution set and set of real numbers, the solution set would definitely begin by x belongs to, I can say, negative infinity right up till 1. I'll keep it 1 at this point. If I have to represent this one, only this way I can represent this one. I can represent. Otherwise, other ones we normally don't represent in real line, or even if you represent, we probably let write as the values like this. But generally, for the for numbers, the real numbers, I can say this is mark 1 somewhere, infinity, negative infinity, and then circle this one, and do not darken, but darken the area to the left of it, and just draw a little arrow indicating that you have the solutions all over on the left hand side, infinitely many values. So this is what the this is how you solve the inequality. Let's take up another question. Let's say second one, solve. Now when I say solve, I generally mean that solve instead of real numbers. Let's say you have minus 5x, negative 5x, plus 3 is, let's say, less than 8. I can say negative 5x here is less than 8 minus 3. Therefore, negative 5x is less than 5. Remember, transposing this one to the other side is actually as good as subtracting 3 on the either side. Whenever you subtract, the inequality is not disturbed on the either side. That's why it remains as it is. So if you're transposing by way of addition and subtraction, don't you worry, just transpose. So you'll find that now comes the trouble. So you're now trying to divide both the sides by negative 5 to get rid of negative 5. So it becomes x is, the inequality will not be the same. It becomes 5 divided by negative 5. So whenever you divide by a negative number, the inequality will always switch around. In order to get rid of this -5, you have to divide both the sides by -5. So it's basically you had -5x by -5 here. It's cancelled. And you're dividing, therefore x becomes more than -1 here. So therefore we find that the solution set is, therefore x belongs to, I can say, -1 to infinity here. So this is what it is. If you represent by number line, this is -1 somewhere, this is infinity, this is negative infinity here, and you have a circle, don't darken the circle, and then you have a region which is going like this, and then this is all the solutions in this area. Talking about, let's say we take up some more examples just to be clear about this one. Let's say you have 4x plus 3, let's say, divided by let's say 7 is more than or equal to 5. Again, we find that here, first of all, I need to get rid of this fellow here, divide by 7. If I multiply, in order to get rid of this 7, I multiply both the sides by 7. So it, like, if you have something divided by 7 is equal to 5, you obviously multiply by 7, so it becomes, this number becomes equal to 5 times 7. So again, this is called transposing. Basically what you're doing is that you're basically getting rid of the 7 by multiplying by 7 and multiply by 7 on both the sides. This cancels out. This is how it appears here. Same way here, when I have something divided by 7 is more than or equal to 5 or something, so I multiply by 7 and multiply by 7. That's basically cancels here. So like transposing this 7 to the other side. But transposing is to be taken very seriously here. This transposing number, that number which has been transposed, is by transpose by way of multiplication of 7, and 7 is a positive number, so the inequality doesn't get disturbed. So you have 4x plus 3 is more than or equal to 5 times 7. Multiply transposing 7 or multiplying both sides by 7, and 7 is a positive number, so inequality remains as it is. So you have 4x plus 3 is more than or equal to 35. Now transposing this 3, so you find that 4x is more than or equal to 35 minus 3. Therefore 4x is more than or equal to 32. Now you find that again, to get rid of this 4 here, I must divide both sides by 4, and 4 is a positive number, so inequality will not be disturbed. So you divide by 4, you find that x is more than or equal to 32 by 4, therefore x is more than or equal to 8. Therefore you find that x belongs to, or the solution set is 8 to infinity. Always write the smaller on the left side here. So if you represent this one, the solution set is somewhere mark 8 here. This is negative infinity, this is positive infinity here, and then more than or equal to 8. So circle this one, darken this one to indicate that that is also a value to be counted for the solutions here. And of course you have the values which are going like this. These are all the values. Just draw a little arrow indicating that everywhere on the right hand side you have solutions. So this is what the inequality is. Let's take up a little different one this time. Let's say fourth one. You take let's say x by 3 minus x by 4 is less than, let's say, x by 5 plus a quarter, where you have x on both sides. So you find that whatever you're doing on the left hand side, the right hand side doesn't know about it. So you can always, if you want, you can always transpose this one. So x by 3 minus x by 4 minus x by 5 is less than 1 by 4. Transposing by way of subtraction or addition does not disturb the inequality. The inequality remains as it is. Therefore, I can take the LCM here. So it says 20 is the LCM. No, not 20. 12, 60. 60 is the LCM here. So take the LCM 60. So you have the 3 times 20, so 20 times x. minus 4 times 15 is 15 times x here, minus 5 times 12, 12 times x here is less than a quarter. Therefore, 20 minus 15 is 5, 5 minus 12 is equal to minus 7 times x by 60 is less than a quarter. So therefore, if I transpose, if I negative 7 times x is less than 1/4 of 60. So I'm transposing a positive number. In other words, mathematically, I'm multiplying both the sides of the inequality by a positive number. So the inequality is undisturbed, remains the same. Therefore, you find that negative 7 times x is less than, for 1s and for 15s, less than 15. But I'm now dividing by a number which is negative 7 in order to get rid of this x coefficient with x here. So if I divide with that, so you'll find that x, immediately the inequality will reverse, and then this becomes greater than 15 by negative 7. Therefore, x is greater than negative 15 by 7. So you'll find the solution set, therefore x belongs to negative 15 by 7, open, and to infinity here. So you'll find that this is negative 15 by 7 somewhere, this is negative infinity, this is positive infinity here. So we have a open interval here, keep it open, and then darken the area beyond, indicating that you have this as this is the solution here. Clearly, a hole is created to indicate that that value is not inclusive, but everything else is inclusive here. Let's say we solve inequality where there is more than line where there's more than one inequality. Let's say question 5 is, let's say you have 5 less than x minus 3 divided by 4 less than 10. So I need to extract the value of x if x minus 3 by 4 is between 5 and 10, then what should be the value of x? No big deal. It's just like ordinary inequality. Supposing you had to put off this side here. Suppose you put off this side completely. Let's say I completely put off this side here by, for a while, I'll just assume that this nothing was here. Then what happens is that in order to get rid of this 4 here, I would have multiplied 4 here. So I would get 20 is less than x minus 3 and multiplying by positive. And again, if I have to put off the other side there, supposing I put off this one here, then 4 would have gone there. So you have x minus 3 is less than 40. In other words, in simple words, I can say that, in simple words, I can say that here, I can multiply throughout by 4. Yeah, that's fair. 4 is a positive number. So you multiply throughout by 4. I would have got 20 is less than x minus 3 is less than 40. Now, in order to get rid of this 3, what I'm trying to say is that earlier, what I was trying to say that be fair to the entire inequality. Whatever you do on the one side must go on the other side also there. So then you need to get rid of this negative 3 here. So negative 3, you add throughout the inequality. So you know that if A is less than B, less than C here, and if you're adding 10 throughout, then A plus 10 is less than B plus 10 is less than C plus 10. That's fair. If you look at two parts at the same time, then it is very fair actually. So you find that therefore 20 plus 3 here, therefore 20 plus 3 is less than x is less than 40 plus 3 here. Adding throughout, so inequality is not disturbed. So you find that this becomes 23 is less than x less than 43 here. Therefore you find that x belongs to open 23 to 43 here. So you find that x lies here. This is 23, this is 43 here, this is infinity, this is negative infinity here. So the values are between 23 and 43, inclusive of the, not inclusive, I mean excluding the 23 and 43, all these values out here. So that's the what is it, the inequality. That's how you handle the inequality where you have more than one of them. Let's say 6th one. Let's say you have something like this. Something like let's say you have minus 3, negative 3 is less than 5 minus 3x divided by, let's say, 4 is less than or equal to, let's say, 8, something like this. Again, you find that I have to first of all multiply by 4, and multiplying by 4 throughout is not disturbing inequality. So you find that negative 3 times 4 is less than 5 minus 3 times x is less than or equal to 8 times 4 there. Therefore, you find that negative 12 is less than 5 minus 3x is less than or equal to 32. Now I need to get rid of the constant part from here, it's 5. So how that will go is you subtract 5. So you subtract 5, you subtract 5. That is subtracting throughout, removing 5 throughout. So you have minus 12 minus 5 is less than negative 3x is less than or equal to 32 minus 5. Yay. Therefore, minus 17 less than negative 3 times x is less than or equal to 27. Yeah, now I have to get rid of this negative 3 here. So if you look at 1 by 1 inequality, if you hide the right hand side part there and then look at this one, you'll find that the inequality will switch. So if I divide throughout by negative 3 here, I'm dividing throughout by negative 3, the inequality will switch around. So you'll find that negative 17 by negative 3 is more than x is more than or equal to 27 by negative 3. The inequality switches around. Lesser becomes more. That is 17 by 3 is more than x, more than or equal to minus 9. We never write the inequality finally in that form. The least always comes the first. So I have that this fellow is the least one here. I'll write first and then this one and this one. That's the right order of writing the inequality. So you have negative 9 is less than or equal to x is less than 17 by 3. Yay. Therefore, you find that x belongs to negative 9, comma 17 by 3 here. So this is how where the values are found. So if you want to locate them, so you can write as negative 9 somewhere and 17 by 3 somewhere and positive infinity, negative infinity here, negative infinity, and you circle this one and darken this area here, and you just circle this one and then you darken the area in between. So this is where the solutions will be found. Infinitely many solutions are found. So let's take up some more. Let's say you could call this as a system of inequalities. But this system is kind of written in a way that this number lies between the other numbers. So I could write the system very well. This is basically, if you split this one, this is basically a system which can be read as solve for x, where minus 3 must be less than 5 minus 3x divided by 4, comma, and comma is as good as and. 5 minus 3x divided by 4 must be less than or equal to 8. So it's basically a system where you have something more than negative 3 and the same thing is less than or equal to 8. So I could write this as a sandwich like this here, this form. But some of the systems could not be written like this. Like, for example, someone says that solve the system of inequalities. Let's say the seventh problem, inequalities. Let's say x minus 3 by 4 is less than 8. And let's say 2x plus 1 divided by, let's say, negative 3 is less than 9. So I can't really merge them anyways because they are different ones actually. So I need to find out the value of x which will obey or satisfy or agree with both the inequalities here. So I'll take up one by one and let's say what's in store. Before that, supposing, let's say I tell you that x is less than 10 and the system has two parts where one part comes out with x is less than 10, the other part comes up with x is less than 15, and you got to conclude a solution for the system of equation. What would you write? If x has to be less than 10 and x has to be less than 15, what would your conclusion be? Actually, if x has to be less than 10, this is 10, and this is 15 here. If you have to stay to the left of 10, and also you got to stay to the left of 15, then you'd better stay to the left of 10, because whenever you stay to the left of 10, you already stayed or you readily stayed to the left of 15. So this will force you to have the conclusion is x is less than 10, because whenever x is less than 10, you actually kind of satisfy the other condition, namely x is less than 15. Yeah. So supposing you have, let's say, x is more than 50, and let's say, and is given thing as comma, x is more than, let's say, 90 here, what should the value of x be? So if you're to agree with both the conditions, then you better stay, this is 50 and this is 90. If you have to be to the right of 90 and if you have to be to the right of 50, then you better be to the right of 90, because if you are more than 90, then you are definitely obeying the condition that x is more than 50. But if you conclude saying that, hey, this one implies that x is more than 50, then this is not true, because x may be more than 50. The value, namely x equal to 60, is very much more than 50, but then doesn't obey the condition that it is more than 90. So if you have to be more than and more than, you choose a value which is greater to tell you that, it's something like this. Let's say college admission, let's say some college admission, there's a condition that, okay, the aggregate mass, if you want to apply, you have to pass, and let's say pass mark is 40% or 50% aggregate in your exams, 50%. And also they put another condition that in order to in order to be able to apply for this particular course, first of all, you have to pass, you have to get less than 50% aggregate, and you must also have more than 95%. First of all, they don't want failures to get in. And secondly, that means they say you have to pass and you must get more than 50%, and you must also get more than 90%. Then if you have got 60%, then obviously they're not going to take you. Actually, you have satisfied the first condition, but you didn't satisfy the second condition. So only if you have aggregate more than 90%, then you go and apply, because though there are two conditions, one condition probably they said, okay, by failing, don't come here, or if you fail or something. And if you have more than, so I don't know how you should see this, but if x is less than 10 and x is less than 15, then x is must be less than 10. And if x is more than 50 and x is more than 90, then x must be more than 90 here. In the practical problems, you'll see the actual use, or how it actually makes sense. But yeah, it does make sense. So you find that here, I'll go to the first one here. You'll find that x minus 3 is less than 8 times 4. Therefore, x minus 3 is less than 32. Therefore, x is less than 32 plus 3. Therefore, x is less than 35. And here you have that 2x plus 1 is more than dangerous, 9 times negative 3, because you're multiplying both the sides by, a negative, the inequality will reverse. Therefore, we find that 2x plus 1 is more than negative 27. Therefore, 2x is more than negative 27, negative 1. Therefore, 2x is more than negative 28. Therefore, x is more than negative 28 by 2. Therefore, x is more than negative 14. So satisfying both the conditions, that is x must be less than 35 and x must be more than negative 14. So I can say the value of x must be between, it must be no more than negative 14, and it must also be less than 35 here. So I can say the ideal value of x, or the values of x that I can look for, are between negative 14 and 35. Therefore, I can say the solutions are found in negative 14 to 35. This is where you will agree with, or you will obey both the conditions here, or the entire system. So when you subject the values to the system, this is what comes out actually. So if you have a machine here, where you program a machine with two conditions, that the first condition here, there is a first condition here, and the second condition here, first condition, second condition, program it very well, and say that, okay, the values that you are looking for are between minus 14 and 35. Minus 14 and 35 here. So let's say you have the solution, let's say they say solve, example number 8 or something. They say solve, let's say, have solve the system of equations. 5x minus 1 divided by 2 is less than 1, comma, 2x minus 3 divided by 7 is more than 15. Let's say more than 15. I have to abide by both the, I have to obey or find a value of x which satisfies both the conditions. Therefore, you have 5x minus 1 is less than 2, multiplying by 2 on both the sides, or transposing 2 to the other side does not cost you anything. The inequality is not disturbed. So you have 5x is less than 2 plus 3. Therefore, sorry, 2 plus 1. Therefore, you find that 5x is less than 3. Therefore, x is less than 3 upon 5. This is what this one says. And then the other part of the inequality says that, then the part of the system rather, says that 2x minus 3 is more than 15 times 7. Therefore, 2x is minus 3 is more than 105. Therefore, 2x is more than 105 plus 3, adding. Therefore, 2x is more than 108. Therefore, x is more than 108 divided by 2. Therefore, x is more than 54. Yeah. Here is the value of x that you want, which has to agree with both the conditions, because the system here, system of equations, you have to find the value of x which is less than 3 by 5 and which is more than 54. If you now check the real line, you'll find that 3 by 5 is somewhere here and 54 is somewhere here, and you're looking for someone who is more than 54 at the same time less than 3 upon 5. So you're looking for, it's compulsion actually, and comma. So you're looking for x to be less than 3 by 5, and you're looking for x to be more than 54. It's not an option. You're not looking for or. This one and that one, you'll find that such x is not possible. So such x, or such value of x, such x does not exist. Does not exist. Therefore, I can say the solution set is null set. You can write as null set like this, or like this. It's null set. You don't find solutions kind. So if you are doing some kind of experiment, you're looking for a kind of an element which satisfies these two conditions, maybe in pressure or temperature or whatever it is. So if you are looking for a value to be satisfying less than 3 by 5 and more than 54, then such a value is not possible. So you cannot have the value which is like this. So yeah, so sometimes it needs a courage to say that, okay, there is no solution. So don't think that every system that you're looking for or you've designed maybe it's a mathematical model actually which you have designed, and then looking for solutions. So sometimes you may not have solutions at all. Maybe you're strongly believing that there must be solutions. Maybe you're missing on some kind of conditions or some kind of conditions in the mathematical model of your model, whereby it is not giving you a solution. But then sometimes you need courage to say that, okay, there are no solutions. So just to tell you that the system may not have solutions all the time, and you know that very well. Let's say you have the questions of this kind. Let's say solve 4x minus 1 divided by 3 is less than 3. And let's say you have 3 minus 5x divided by 2 is more than 1, maybe, let's say this one. If 4x minus 1 is less than 9, therefore 4x is less than 10, therefore x is less than 10 by 4, therefore x is less than 5 by 2. So 3 minus 5x is more than 2, therefore minus 5x is more than 2 minus 3, so minus 5x is more than negative 1, therefore x is less than negative 1 by negative 5, so x is less than 1 by 5. So here x is less than 5 by 2, 1 by 5 is somewhere here, and 5 by 2 is 2.5 somewhere here. So if you're looking for a value of x which is less than this and also less than this, then you look for a value which is commonly satisfied by you have this one and you have this one. Therefore, the only value that you can look for is that therefore x must be less than 1 upon 5. Conclusion. So if you choose the value of x which is less than 1 upon 5, you're readily satisfying the condition that it's less than 5 upon 2. But if you conclude that, oh, the conclusion is x is less than 5 upon 2, there are so many values in this range here, in this location here, you'll find that they don't abide by the less than 1 by 5 condition. That's why if you are choosing a value to the left of two distinct values, then you choose the value which is less than the lesser one, because when you are less than the lesser, you definitely less than the greater number that you have in inequality there. So you can say that therefore the solution is that x belongs to negative infinity right up till 1 upon 5 with the open interval here. So is a condition. So talking about some of the word problems, just pick up a few problems where there are sentences and problems which involve some kind of inequalities in them. Let's see. Let's say you have a condition like this. The question goes like this. The IQ of a person, IQ of a person is given by the formula. IQ is equal to mental age by chronological age multiplied by, let's say, 100. Of course, MA is the mental age and CA is the chronological age. If 80 is less than IQ is less than 140, this is IQ between 80 and 140. For a group of 12-year children, find the range of their mental age. All right. So the IQ is between 80 and 140 for a group of 12 years children. So 12 years is like, that's the chronological age, the actual age of them in terms of years. So if that is a case, then what should be the mental age? So I can say that here, I can say that the IQ is between 140 and 80. Therefore, I can say mental age by chronological age multiplied by 100 is less than 140 and more than 80 here. So they've given us the age of the children, that's the chronological age. Therefore, I can say 80 less than mental age divided by 12 multiplied by 100 is less than 140. I can multiply throughout by 12, which is positive. Therefore, you have 80 multiplied by 12 is less than mental age multiplied by 100, less than 140 times 12. I can divide throughout by 100. Therefore, 80 times 12 upon 100, and 100 is positive, so I can always divide. Less than mental age is less than 140 times 12 upon 100. 0 and 0 cancels. 0 and 0 cancels here. Therefore, you find that 96 by 10 is 9.6. Less than mental age is less than 16.8 here. Therefore, the mental age of children is given less than, okay. So therefore, mental age of the children is between 9.6 and 16.8 here. So going forward, let's pick up one more question. Let's see, we have all right, a lab problem, lab person's problem. The solution is kept. Let's say solution is kept between 80 degree Fahrenheit and let's say 95 degree Fahrenheit. What is the range of temperature? What is the range of temperature in degrees in degrees Celsius if the conversion formula is Fahrenheit is equal to 9 by 5 times C plus 32. So supposing, let's say you're handling the acid and then you go to see, okay, you don't know this Fahrenheit and your thermometers show temperature scales in centigrades, Celsius, and then the very strict instructions there, this liquid must be maintained between these Fahrenheit temperatures. Maybe beyond that, it'll kind of burst or some, maybe it'll leak or whatever it is, I don't know. So let's say this is the instruction. So you have to store between these Fahrenheit here. So what is the temperature in Celsius? So I can say Fahrenheit is between 95 and 80. Yeah, usually between is, when we say between, it's like greater than or less than, but you may also think about, the less than or equal to or more than equal to, not a big deal. But between is usually when you say how many people are sitting between, let's say this is Aaron and this is, let's say, Tim or something, and there are people here sitting. Mathematically speaking, when say between, how many people are sitting between Aaron and Tim? So we say it's 3. Actually, we don't count Aaron and Tim. Actually, yeah. Anyways, keeping that in mind, so it's less than. So you have 9 by 5 times C plus 32 is less than 95 and more than 80 here. So I subtract 32. So 80 minus 32 is less than 9 upon 5. times C is less than 95 minus 32. Therefore, 80 minus 32 is equal to 48. Yeah, 48 is less than 9 by 5 times C is less than 5 minus 2 is 3 and 9 minus 6 is 63 here. So I multiply by 5. So if I multiply by 5, it's fine. So 48 multiplied by 5 is less than 9 times C is less than 63 times 5. I divide by 9. You'll find that 48 times 5 upon 9 is less than C is less than 63 times 5 upon 9. Okay, therefore, 3 threes are and 3 16s are here. 16 fives are 80. Yeah, I missed something. 18 minus 32. Okay, all right, it's right. So less than so much. 9 ones are 9 sevens are. Therefore, you find that 16 fives are 80. 80 by 3. So 80 by 3 is less than C is less than 35 degree Celsius. So I can say the degree Celsius must be, therefore, it must be stored between 80 by 3, whatever the mixed fraction is. So many degrees Celsius and so many degrees Celsius. This is where you should be storing that, the instructions which come label which says that store between these ones. Now in your lab, you'll replace that label by store between 80 by 3, 80 by 3. 3 2s are 6 and 2 carry 20, 3 6 are 18 here and 2. So you'll say, therefore, store between 26 2 by 3 degrees Celsius and between this and 35 degrees Celsius in order to avoid any danger that can be caused by the excessive cooling or overheating or something. So this is the temperature between which you should store your liquid. Right. So supposing, let's say you have a problem like last problem, and then we can stop this recording. So let's see, the next question is that here you have, let's see, you have, yeah, a manufacturer, has 600 liters of 12% solution of acid. How many liters of 30% acid solution must be added to it so that the acid content in the resulting mixture will be more than 15%, but less than 18%. Yeah. What they're trying to say is that someone is having 600 liters of 12% acid. Yeah, 600 liters of 12% acid. Now they're mixing, so it's an acid, 600 liters of 12% acid. Now they're mixing some 30% acid. When you add 30% acid to this, concentrated acid. Obviously, and if you keep on stirring, so there's a meter on this one here, meter shows the concentration or something. So you'll find that if you keep on adding something, the tap is open with 30% acid here, you keep on adding to this one, and keep on stirring, you'll find that the concentration meter will keep on showing higher and higher concentration. So if you keep on adding more and more, 12% will show 13%, 14%, keeps on, the concentration keeps on rising because you're adding a concentrated acid. They're saying that how much should you add so that the acid content of the resulting mixture is more than 15%, but less than 18%. Let's say they got an order for the acid. Please send us the acid concentration should be between 15 and 18% for the lab or wherever it is. And you have 600 liters of 12% acid. And you also have another container of 30% acid. How much should you add so that the concentration is between 15 and 18 is the question. This problem is actually sounds similar to, you have, let's say, kind of cold water or something at 20 degrees or 15 degrees Celsius or something. And then you have boiling water tap, or let's say you have another bucket of boiling water, hot water. How much of boiling water should you add into this one so that the temperature of water is just, just warm, let's say more than 25 and less than 35, something, so it's a wash or something. So it makes sense. So if you keep on adding the hot water and keep on mixing it up here, you'll find that the 15 degrees Celsius water, cold water, will become warmer and warmer, hotter and hotter. So it becomes, the temperature would rise between 15 and 35. So assuming that there is no kind of loss of heat anywhere, supposing you kind of seal the system. So what I'm trying to say is that here, the adding the concentrated acid to the weak acid and mixing it up, you can bring up the concentration. So I can say this mathematical model as, let's say, I don't know how much should I be adding. Let's say X liters have been added, unknown liters. Saying that how many liters, 30% is added. So when you added X liters here, you'll find that there is, here what happens is that in this container now, you have 600 liters of 12%, plus you have X liters of 30% here. And then that is less than, this is more than, this is 18% of what you have is that earlier you have 600, now you added X liters here, so much of quantity, and more than 15% of, you'll find that you have 600 was earlier, and then you added X liters. So 15% of the total quantity here is less than the total concentration like this, 18% of total quantity. So the whole model comes out like this. I can say that 15% of 600 plus X here is less than 600, or I can say 12% of A% of B is same thing as B% of A. So 12% of 600 plus 30% of X here is less than 18% of 600 plus X. So therefore you find that 15 out of 100, how much out of 600 plus X here is less than 12 out of 100, how much out of 600, plus 30 out of 100, how much out of X here, plus, sorry, less than 18 out of 100, how much out of 600 plus 600 plus X here. So you can always choose to multiply throughout by 100, and because 100 is a positive quantity. So if you multiply each term of the inequality by 100, you'll find that 15 times 600 plus X is less than 12 times 600 plus 12 times 600 plus 30 times X here is less than 18 times 600 plus x there. Therefore, you find that 15 times 600 plus 15 times x is less than 12 6 72, or 12 times 600 plus 30 times x is less than 18 times 600 plus 18 times x. Now I deal with this inequality here and also deal with this inequality here, and then because there's x scattered everywhere, so if I go with this one, I cannot consider this as another inequality. So you have 15 times 600 plus 15 times x is less than 12 times 600 plus 30 times x here. Therefore, I can say 15 times x minus 30 times x is less than 12 times 600 minus 15 times 600 times 600 here. So therefore, minus 15 times x is less than 12 times something minus 15 times the same thing is equal to minus 3 times 600 here. So I can divide by negative 15. Therefore, you'll find that x is more than, beware, the inequality will reverse. Negative 3 times 600 divided by negative 15 here. So 3 ones are 3 5s are, and 5 ones are 5 12s are 60, 120. Therefore, x is more than 120. So this is what comes out with this one. So if you go with this one here, you'll find that 12 times 600 plus 30 times x is less than 18 times 600 plus 18 times x there. Therefore, 30 times x minus 18 times x is less than 18 times 600 minus 12 times 600 there. Therefore, you find that 12 times x is less than 18 times something minus 12 times the same thing is 6 times 600. Therefore, x is less than 6 times 600 divided by 12. 6 ones are 6 twos are 2 ones are 2 threes are 300. Therefore, x is less than 300. So x must be more than 120 and less than 300. So you must add more than 120 liters of liquid. Therefore, more than I can say here now. Therefore, the number of 30% number of liters of 30% acid must be more than 120 liters, 120, but less than 300. So if you are opening a tab, make sure that you're more than 120 and less than 300, then you would have satisfied the customer who wanted the solution with concentration between 15 and 18 there. I hope you understood all this. In the next video, I will cover modulus inequalities and so on.